Okay, so in this second part, we will mostly use this optimal stopping theorem in this form for the expectations, and we will look at some applications to random walks, and in particular to heating time and crossing times for random walks. Okay, let's start with a simple example first of, well, it's called a simple random walk. Okay, so here we will consider IID Bernoulli random variables. So we'll have a sequence xi, which will be IID, and xi's will take two values, plus and minus 1, with probabilities p and 1 minus p. Okay, which we will also denote by q. Then we'll consider the following sequences. Will be just a sum of these x's from 1 to n. Okay, so this represents a random walk where at each time n you take a step equal to xn. And in this first example, we will consider the following stopping time. So we'll consider some numbers a and b, where a will be negative and b will be positive. Now these will be integer numbers, and then we'll consider the following stopping time tau. Right? It will be just the first time when our random walk starting from 0 reaches one of these levels, a or b. Okay, so you can imagine this picture here where you have some level b above 0 and some level a below 0, and you start from 0, and you're taking some steps until you hit one of these numbers, a or b, and that's the stopping time tau. Now what we want to know, or what we'll compute using the optional stopping theorem, is the probability that you hit a first or b first. Okay, and this will be done by considering the following two martingales, depending on whether our steps are symmetric, so p is equal to 1/2 or not equal to 1/2. In the first case, when p and q are equal to 1/2, so in this case we know the expectation of the step is 0. So we have already seen this example that the sum itself will be a martingale, where in this particular case, or from now on, we just think of the sigma algebras Bn as generated by the sequence itself. Okay, so this is a martingale when the expectation of the step is 0. The first stopping time is just equal to 1, so it's just a constant, and the second stopping time is just this tau. Okay, now I'm going to leave it as an exercise to show, it's a simple exercise to show that the stopping time here will be finite with probability 1. And also notice that since here we have two boundaries, if n is before the stopping time tau, that means your walk has not reached a or b. So in particular, the Sn here is bounded by the maximum between b and the absolute value of a. So the integrability conditions in the optional stopping theorem are kind of trivial in this case. And so as a result, we can write that the expectation of our martingale at the first stopping time, namely at 1, so that's just the expectation of x1, which we chose to be 0, it will be the same as the expectation of the stopping time at or the martingale at this stopping time tau. And this has two possibilities, right? Either this sum is equal to a, with the probability that you reach A first, or it's equal to B with the probability that you reach B first. And as I said, the exercise will show that these two probabilities add up to 1. So you have to stop in a finite amount of time with probability 1. So the sum of these two probabilities will be 1. So as a result, you can just write this in terms of the probability that you reach A first. So plus B times 1 minus the probability that you reach A first. And then you can solve this for the probability that at this stopping time you'll be in the position A. Okay, and this will be just, if you solve this equation, you'll just get B over B plus absolute value of A. Okay, and as a result, the probability that you reach B first, this will be absolute value of A over B plus absolute value of A. All right, now in the second case, when P is not equal to 1/2, so the expectation is not 0, we consider the following martingale. So here we'll consider yn, which will be q over p to the power Sn. Okay. Now if p and q were both 1/2, this would be just 1, so this would not carry any information. But when p and q are not equal, this is kind of a non-trivial martingale. And the reason this is a martingale is very easy to check. Namely, you want to see that the average at the step n+1 conditionally on your information up to time n. So in other words, on the values of your x's up to time n. Well, because the last step n+1, it's independent, and you're just averaging with respect to the last step, and so you know that with probability p, you will go one step up, right? So the value of yn+1 will be q over p, the position at time n plus 1, okay? And the position in time n is measurable with respect to bn, so I am treating it as a constant. And with probability q, you will go down by 1. So this will be q over p Sn minus 1. Okay. And if you just cancel this power plus 1, so q over p times p will be q, and the second one similarly, so you will just see that this is q over p to the Sn, which was exactly yn. Okay, so this is a martingale, and we'll see it actually fits into a more general family of martingales in a second when we discuss the fundamental Wahl's identity. But here, this is a martingale, and so we are going to apply the optional stopping theorem again to time 1 and tau. Well, you can actually start at time 0 here. So at time 0, the sum is 0, so the martingale is 1. So the expectation of y0 is just 1. And then, okay, assuming that the conditions in the integrability conditions in the optional stopping theorem are satisfied, you want this, this will be equal to the expectation of y at the stopping time tau. And then again, you have just two possibilities. So either you hit A first, so then this will be q over p to the power A times this probability that you hit A first, or this will be B if the sum at that stopping time is B, so you hit B first. Okay, and again, these two probabilities add up to 1 for the same reason, so it's the same exercise, that the stopping time here is finite, and so you can solve this for, let's say, the probability that you hit B first. Okay, it will be q over p to the A minus 1 over q over p to the A minus q over p to the B. Okay, and then you can similarly compute the second probability. Okay, and then the condition in the optional stopping theorem is satisfied again for the same reason that I said before, that before the stopping time your sum is somewhere between A and B. So the condition that we have to check is that the expectation of this yn on the indicator, that n is before the stopping time, right? We want to make sure that this goes to 0 when n goes to infinity. Okay, and y here is, well, it's non-negative the way we define this martingale, but the main point here is that the power Sn before the stopping time, it's between A and B. So basically here you can put either plus minus A or plus minus B. Okay, so yn is bounded by some absolute constant before you reach that stopping time tau, and as a result you're really asking here that the probability that tau is greater than n goes to 0, and that's the exercise that I mentioned. All right, so here we use the stopping time to compute the probability that you hit one of these two boundaries first. So in the next few examples we will make the following assumption. So first of all, we'll always be in the same setting when we take IID steps in the random walk, so xi's will always be IID. So we'll consider S0 0, and as before, Sn will be just the sum of these increments up to time n. And the assumption that we are going to make here is that the Laplace transform of one step is defined in the neighborhood of 0. Okay, so we'll assume that the Laplace transform phi of lambda, which is expectation of e to the lambda x1, okay, it's bounded, it's well defined in some neighborhood of 0. So for lambda in between lambda minus and lambda plus, which contains 0. Okay, so we make some assumption on the tails of the distribution, so these exponential moments are defined near 0. Okay, and the martingale that we will consider will be a generalization of the martingale in the previous example. So here yn will be e to the lambda Sn divided by this Laplace transform to the power n. Okay, and we consider this martingale for any fixed parameter lambda where this expectation, this Laplace transform, was defined. So for any lambda in this interval. Now, in the previous example, we simply took lambda corresponding to the values, so corresponding to where this Laplace transform, so Laplace transform in that case of a plus and minus 1 random walk is just p e to the lambda q e to the minus lambda. Okay, and if you set this to be equal to 1, you can see this corresponds to e to the lambda equals to q over p. Okay, so that's why the yn there, q over p, so this is just e to the lambda to the power Sn, and you divide by 1 because that's where Laplace transform is 1. That was just one possible choice of the value lambda in this family of martingales. Okay, and in any case, for this particular martingale, we will use the optional stopping theorem in the form of for the expectation as above. So let me just write it one more time here. The first stopping time will be just 0. So we'll start by saying our martingale y0 at 0 is 1. And then the equation above for the expectation was saying that this is equal to the limit of the expectation of y at the stopping time tau on the indicator that the stopping time is less than or equal than n when n goes to infinity. Okay, if and only if. So the integrability condition is that the limit when n goes to infinity of the expectation of yn on the indicator that the stopping time is greater than n is equal to 0. And in this particular case, the martingale is non-negative. So this yn that we defined here, it's non-negative. And so as a result, in this first limit here, you can just use monotone convergence theorem. So by monotone convergence theorem, the right-hand side of the first equation is just the expectation of y tau on the indicator that the stopping time is less than infinity. So the stopping time is a proper random variable. And by the way, I said that this is a martingale here, but I did not repeat the same calculation we did above, but obviously it's a martingale, right? If you look at the time n+1, when you take expectation in the last step, in the numerator, you'll just get a Laplace transform, so one of the factors in the denominator cancels. So it's exactly the same calculation as before, showing that that's indeed a martingale. And this equation here, so maybe let me just rewrite it. Okay, so let me remove the middle steps and just rewrite the above equation as 1 equals to the expectation of y tau, where, let's recall, y tau is e to the lambda, the random walk at the stopping time, over the Laplace transform to the power tau on the indicator where tau is less than infinity, of course under this integrability condition here. Okay, and so this very important equation that we obtain here is, it has a name, okay, and this is called fundamental Walls identity. Okay, in particular, we can see here that it gives some kind of very strict relationship between the stopping time and the value of this random walk at the stopping time. Actually, in most of the examples, there will be some special information about the sum, so that will give us information about the stopping time itself, or the distribution of the stopping time itself. By the way, this equation here, it is related, so it looks kind of different from the Walls identity that we have seen in one of the previous chapters for the sum up to a stopping time. But it's actually something more general here, although under stronger assumptions. Okay, so in particular here, if, let's say, if we also know that the stopping time is finite, so the equation will be just 1 equal to the expectation of e to the lambda s tau over phi lambda to the tau. Again, assuming the integrability condition is satisfied. Then you can check that if you take the derivatives of both sides in lambda at lambda equal to 0, okay, what you will get formally is exactly expectation of s tau is equal to the expectation of x1 times the expectation of tau. Okay, so this fundamental Walls identity contains the Walls identity for the sum, but of course this Walls identity for the sum was proved just under the assumption that the expectations are finite, while the above identity, we already assume a lot more about the distribution of x. Now, the integrability condition here, okay, sometimes it may be difficult to check, or sometimes it may be easy to check. So we'll see kind of in a second, we'll see a different point of view when you can get Wald's identity for certain values of lambda kind of directly, just with the right interpretation of this identity. In many cases, you can see this identity sort of directly. But first, let's take a look at another application to the symmetric random walk. Okay, so let's look at, again, an example for the simple random walk, but in this case, it will be also symmetric. Okay, so in other words, we are considering IID random variables xi taking values plus and minus 1, but now it will be with probability 1/2. And moreover, in this particular case, we'll consider a symmetric boundary. So we'll take some number a, or integer a greater or equal than 1, and the stopping time that we'll consider here will be hitting the boundary minus a or a. So the boundary, two boundaries now will be symmetric around 0. So this tau will be a minimum of k greater or equal than 1 when your random walk reaches either minus a or a. And in this case, we'll see that the fundamental Wald's identity will actually give us the entire distribution of the stopping time. So first of all, the Laplace transform here is just 1/2 e to the lambda plus 1/2 e to the minus lambda. So this is just a hyperbolic cosine at lambda. Okay, and we'll use in a second that hyperbolic cosine is always at least 1. And in particular, the integrability condition above that we need to check is that our martingale e to the lambda at time n, so e to the lambda Sn over phi of lambda n, on the indicator that stopping time is greater or equal than n, right? We want this to go to 0 when n goes to infinity. And again here, the stopping time is greater than n, which implies that the sum at n has not reached a or minus a yet, right? So the numerator here will be at most e to the, some constant, right? E to the, let's say, absolute value of lambda times a. And the denominator is hyperbolic cosine, so it's at least 1. So if I remove the denominator, we'll just get something bigger. And so we are left with again, probability that the stopping time is greater or equal than n, which from the above example, we already said that this will go to 0 when n goes to infinity, right, from one of the exercises. So this condition holds, so that means that we do have this fundamental Wald's identity here, that 1 is equal to the expectation of e to the lambda random walk at the stopping time over phi lambda to the stopping time. Okay, but because of the way we chose the random walk to be symmetric and the boundary to be symmetric, we can actually simplify this right-hand side quite a bit. Okay, that if you look at the right-hand side, you can break this into two possibilities, that you reach the boundary a first, in which case the sum will be a, right? So you have e to the lambda a in the numerator, okay, and then you just have the denominator, I'll leave it as it is, on the indicator that you reach a first. And then similarly, if you reach minus a first, your numerator will be e to the minus lambda a, and so the rest is the same on the indicator that you reach minus a first. But these two integrals here, okay, they are actually, if you look at this integral and this integral, they are equal, right, by symmetry. Because the random walk is symmetric, so if you replace, steps x by minus x, it's still the same random walk, and replacing x by minus x, it's equivalent to replacing a by minus a. So by symmetry, these two integrals are actually equal, and in particular, they are equal to their average, right? So, and their average, right? So what is their average? Their average of those two integrals is just 1/2 of the expectation of 1 over phi lambda to the tau, and then the sum of two indicators is just 1, because we know that you will have to reach one of the boundaries eventually. Okay, so actually both of these integrals simplify, and as a result you just get 1/2 e to the lambda a plus e to the minus lambda a, which is just a hyperbolic cosine of lambda a times the expectation 1 over phi lambda, but here I'm using the fact that phi lambda is hyperbolic cosine of lambda to the t. So everything here simplified because of this symmetry, and we got rid of the random walk at time tau, and we are just left with the stopping time itself. So in particular here you can make the change of variables for negative gamma, right? Because hyperbolic cosine is bigger than 1. You can find such a lambda for any gamma less than or equal than 0. And the equation will become hyperbolic cosine of this lambda. Well, I'm not going to solve it, but here you have to solve for this lambda in terms of gamma, but I'll just leave it like this. And the second term will be e to the gamma tau, right? And this whole thing was equal to 1. We started with 1. So in particular, we get that the Laplace transform of the stopping time can be explicitly calculated as 1 over hyperbolic cosine of lambda a, where lambda is defined by the above equation, right? Where e to the gamma is 1 over hyperbolic cosine of lambda. But of course, something special was used here in combination with Wald's identity, right? We used these symmetries and special information about the value of the random walk at the stopping time. Okay, we'll give a few more or a couple more examples in the same spirit as this example below, but first I want to discuss the fundamental Wald's identity, and one way that you can see for certain stopping times that the fundamental Wald's identity holds without checking the integrability condition, at least for some choices of lambda. Okay, so the identity that we want here is 1 equals to the expectation of this martingale e to the lambda s tau over phi lambda to the tau on the event that tau is proper random variable, right? So we want to know whether this identity holds, and one criterion is just that integrability condition, but sometimes you can just see it a little bit more directly if you reinterpret this question using this particular martingale, or thinking of this particular martingale as a change of density. Okay, well, more precisely, if we consider the following distribution, p lambda, which will be defined by the following change of density. So it's simply a distribution which has a density e to the lambda x over phi of lambda with respect to the distribution of x. So here the denominator is just the distribution of this sequence. We call it p. Now it's a change of density because, of course, when you integrate on the real line e to the lambda x over phi of lambda with respect to this distribution, well, that was the definition of Laplace transform. So that was the reason that was a martingale. And so the integral is 1, so indeed this is a density. So you can reinterpret the right-hand side of the fundamental Wahl's identity in terms of this distribution. Namely, if you write the right-hand side above, okay, you can just sum over all possible specific values for the stopping time. So let's take a sum from 1 to infinity of the integral, and let me write it out a little bit more explicitly. So the sum will be x1 up to xn. So because I'm going to take tau equal to n divided by phi lambda to the n on the indicator that tau is equal to n. Okay, and now let's write this out a little bit more explicitly using the distribution of x. So each of these integrals can be written as an integral on Rn. Actually not on Rn, but on this set tau equal to n. Now this set is actually measurable with respect to the sigma algebra Bn, and so let's recall that since it's a stopping time, it's in Bn, and now we always take Bn to be sigma algebra generated by the sequence itself, right? So it's an event expressed in terms of these random variables x1, xn. So indeed I can write as a subset of Rn when we are integrating this function of x1, xn with respect on their sample space, with respect to their distribution p, right? So the first coordinate is px1 and so on. Okay, and now each of these factors e to the lambda xi over phi was just the change of density in the definition of the measure p lambda. So you can think of this as the sum of integrals over these sets of dp lambda x1, dp lambda xn, right? So the martingale just becomes this change of density, and then when you sum all of this back, you just get the probability for the sequence. So it's a product of p lambda over all I from 1 to infinity of the event that the stopping time is finite. Okay, so in other words, since that's the right-hand side of the fundamental Wahl's identity that we want, right? The fundamental Wahl's identity becomes a question whether this probability is equal to 1. Okay, and so it's just a question whether the stopping time tau is a proper random variable when your random variables xi are replaced by, let's say, random variable xi tilde. So if you have this new sequence of random variable which are IID, but they come with this new distribution p lambda, and you define the same stopping time tau in terms of this random variable, the question is whether this stopping time is finite under this distribution with this change of density, right? With probability 1, or almost surely. Okay, so let's look at one example where this point of view is actually very helpful to derive this fundamental Wahl's identity. So in the next actually few examples, we'll be looking at the case of crossing a growing boundary or a constant boundary. So it will be similar to the previous example, but we'll just have one boundary instead of two. So crossing growing boundary. Okay, so let's consider some function on the integers. Okay, and let the stopping time be the first time when our random walk crosses this function f of k. Okay, in the next two examples, we'll actually take this function to be a constant. So this will be just a constant boundary. Okay, but here when we think of this fundamental Waltz identity with respect to this change of density, or from the point of view of this change of density, one thing that we can do is calculate the expectation of these random variables xi tilde with this distribution p lambda above. And this will be just an integral of x, right, with this change of density e to the lambda x over phi of lambda dp. Okay, and then of course what you see here, that integral of x e to the lambda x is just the derivative of the Laplace transform. So you have the derivative of the Laplace transform divided by the Laplace transform, right? And of course this taking the derivative inside the integral here is justified by the assumption that Laplace transform is defined in the neighborhood of 0. Okay, so that's defined for all lambda in some neighborhood of 0. So depending on how fast your boundary Fn grows, you can appeal to the strong law of large numbers to decide whether you will hit this boundary with probability 1. Okay, so if you think of the strong law of large numbers, right, it tells us that this sum tilde divided by n, so in other words, the sum of these random variables x tilde divided by n converges almost surely to the expectation of one of them, right, which is phi prime of lambda over phi of lambda. And so depending on the value of this limit, you know that your random walk grows at least linearly. So in particular, if the boundary Fn grows slower than this rate, so if the lim sup of Fn over n is strictly less than this limit in the law of large numbers, then you know that your random walk will cross this boundary with probability 1. So in other words, under this measure with the change of density, the heating time of this boundary will be a proper random variable, right? Will be finite with probability 1. In particular, the fundamental Waltz identity will hold. Of course, this condition, when you compare the growing boundary, the rate of growth of the growing boundary with this particular value, now this value depends on lambda, so it might hold for some lambdas and not for other lambdas. But one thing that we can notice here is the following, that this derivative of Laplace transform over Laplace transform is actually a non-decreasing function, because the logarithm of the Laplace transform, which is the logarithm of the expectation e to the lambda x1, right, just by Hölder's inequality, this is a convex function in lambda. So when you take the derivative, which will be phi prime over phi, this will be non-decreasing in lambda. So in particular, if the above condition here, right, this condition on the rate of the growth of this boundary holds for some lambda, so if the above condition, let's call it star, holds for some lambda, then it holds for all lambda greater than that. Then it holds for all lambda prime greater than lambda. Of course, as long as you stay within that interval where the Laplace transform is defined. So let's consider now an example of a constant boundary. So fn equals to some positive z, and in the next examples we will look at integer valued random walk. So here we'll take z to be also integer. Now, of course, in this particular case, that the limit that we considered above is just 0 because the fn is constant. So our condition for the fundamental Wald's identity to hold for any given lambda is that phi prime of lambda over phi of lambda is bigger than 0. Or, in other words, phi prime of lambda is bigger than 0. Okay, so if this holds, then the probability under this change of density that the stopping time is finite is equal to 1, which is just a way to rewrite the fundamental Wald's identity. Now, from now on, let's also assume that 0 satisfies this. So lambda equals to 0 satisfies this inequality. Now, what is the derivative of Laplace transform in 0? Of course, it's just expectation of x1. So we have a random walk with some positive drift. Now you can also check that the derivative of this ratio, so we already said that this ratio here is increasing in lambda, but if you look at the derivative of this ratio at 0, then it will be actually equal to the variance of x. So if x is not a degenerate random variable just equal to 0, then this will be not just increasing but strictly increasing at 0. Okay, and by continuity you will also have that if phi prime of 0 is strictly positive, then it will be strictly positive in some neighborhood of 0. Okay, so in particular the Wald's identity will hold in some neighborhood of 0, and since the 0 is included in this condition, right, the stopping time is almost surely finite under the original distribution, and so the fundamental Wald's identity in this case, well, it will be this identity where you can drop the indicator, right? The indicator that tau is less than infinity will have probability 1. That event will have probability 1, and so this is the identity that we can use under this assumption of positive drift and some constant positive boundary. So next, let's look at a couple of examples where we can derive information about the distribution of this heating time from this Wald's identity. And the first example, it will be very similar to the example above, except here we will consider slightly more general distribution. Instead of just a symmetric random walk, we'll consider the steps which can take integer values up to 1. And of course, the fact that the expectation is strictly positive in our assumption, right? This means that it must take value 1 with probability, with positive probability. And the reason we stop at 1 is because, together with our assumption that the boundary is an integer, that means that when we cross the boundary, we have to hit the boundary, right? We cannot jump over this boundary. So when we hit the boundary, the random walk at that time will be just equal to z. And so the Wald's identity can be written in that case as 1 equals to e to the lambda z because of this, right? And then inside the expectation, you are just left with 1 over Laplace transform to the power tau, and again this is true in some small neighborhood of 0. Okay, so that means that we essentially determine the Laplace transform for the stopping time tau, right? Because we get this equation here which holds for lambda in some small neighborhood of 0, and so this gives you Laplace transform for some interval of parameters gamma as above, and so you can get the information about the distribution of tau again. Okay, another example that we'll consider will be for specific types of distributions. One can consider a more general example, but for certainty I will just consider the example of geometric distributions for these steps xi in the random walk. Okay, so in other words, our random variables xi, they will take natural values. Okay, and the probability, so the geometric distribution is the probability that your random variable is greater or equal than k is given equal to 1 minus p to k minus 1, okay, for k starting from 1, 2, and so on. Okay, now the parameter p here is of course some number between 0 and 1. So it's the usual geometric distribution, and then what we'll show here is that in this case the sum and this stopping time when we cross the boundary z will be independent. Now notice here that the geometric distribution can jump over the boundary z, so the position will actually be random, but these two values will be independent of each other, and moreover the distribution of the position of the random walk will be, so this random variable will be equal in distribution to z minus 1 plus just one geometric random variable, let's say x1. So it will have a very specific distribution, and so as a result this information together with fundamental Wahl's identity will again determine the distribution of the stopping time. Okay, so let's do the calculation that shows this last claim. Okay, so if we take, so let's compute a probability that the position of this random walk will be greater or equal than some value y when the stopping time is equal to n. Now, of course, y here can be taken to be greater or equal than z, because at the stopping time you're supposed to jump over z. So again, maybe I should remind here that the tau is the first time when our random walk exceeds z. So to compute the above probability here, okay, let's break it into different disjoint pieces depending on the position right before we cross the boundary. So let's write this as a sum over all possible values less than this boundary z of the probability that s tau, well, tau is n, so I can write Sn is greater or equal than y, tau is equal to n, and then the position right before at time n minus 1 is equal to this x. Okay, now we can rewrite each term here a little bit, because if we know the position right before, then the fact that the position at time n is greater than y means that our last jump xn was greater than y minus x. And so Sn minus 1 is equal to x, I'll just leave it as it is. And in this case, we know that the stopping time must happen before time n, because if we are at position x and then the next jump will cross this level y, which is greater than z or greater than z, then that means that at time n for sure we cross, but it's possible that we crossed earlier. So instead of writing that the stopping time is equal to n, here actually all I need to write is that it's greater or equal than n minus 1. In other words, the stopping time did not occur before position n minus 1. Then by looking at these events here, we know that then it must occur at time n, because we can see that we just crossed the actually level y, which is above z. So we can rewrite it like that. But the reason I wanted to rewrite it like that is because in this form, now this last two events belong to sigma algebra generated by our sequence up to time n minus 1. In particular, they are independent from the event expressed in terms of xn. Okay, these two are independent. So now we can write it as a product of probabilities by independence. And moreover, xn has geometric distribution, so we have a specific formula for it. It's 1 minus p to the power 1 minus x minus 1. Okay, and then we're just left with this probability that Sn minus 1 is x and tau is at least n minus 1. Okay, and then what we do here is we use the fact that y is greater or equal than z. So this is kind of like a memoryless property of the exponential distribution. So we will simply factor out 1 minus p to the power 1 minus z. And then we'll be left with 1 minus p instead of y, right? We just write z minus x minus 1 times this probability. Okay? But this last probability here, right, it's just the probability that the last jump or the geometric random variable is greater or equal than z minus x. Okay? And so we can take, using independence again, we can take this event inside the probability and rewrite it as follows. So the first term is the same here, and then we sum over all x less than z, probability that xn is greater or equal than now z minus x instead of y minus x, and everything else is as before. But then we just rewrite it kind of backwards, the way we arrived to this condition here, namely this last event here is nothing but the event that at Sn minus 1 we are at x, and then tau is equal to n, right? The fact that tau did not happen before n minus 1, and then the last step actually takes us above z, just can be expressed by saying that tau is equal to n, and so the summation over all the x's finally gives us essentially what we want, right? So we get back to the probability that when we sum over all possible x's, that tau is equal to n. So this gives us independence of tau from s tau. So let's recall we started, so this was the probability here that s tau is greater or equal than y and tau is equal to n. So in particular, we proved that they are independent, and probability that s tau is greater or equal to y is equal to 1 minus p to the 1 minus z for any y greater than z. Now, if we make a change of variable here and write this y as z minus 1 plus k for k greater or equal than 1, right? Then we see that this just becomes geometric. So this is 1 minus p to the k minus 1 for k greater or equal than 1. So in particular, that proves what I claim, that S tau has the same distribution as geometric plus the shift z minus 1. So x naught here is geometric as above. Alright, so with this information, what does fundamental Waltz identity tell us? Right? It tells us that 1 is equal to the expectation of e to the lambda s tau divided by the Laplace transform to the power tau. Again, here I don't need to write the indicator because the geometric has a positive drift. It's a non-negative random variable, so we'll cross the constant boundary with probability 1. But now, because we have independence, we can write this as a product, e to the product of two expectations. Okay, and moreover, this first expectation, st is equal to the distribution to z minus 1 plus the geometric distribution. So you're just left with the Laplace transform of this one step, of the one geometric distribution, which in this case, again, you can compute explicitly. I'll just leave it like that. And so as a result, again, we computed, if you make the change of variables, again, we get Laplace transform for the stopping time. Okay, so in this case of geometric distribution, we use the different information. The position of s of our random walk at a stopping time, it was not constant like before. You could jump over, but here we have some special information that it's independent of the stopping time, and moreover, you know precisely what the distribution is. Okay, so that gives us another application of the fundamental Waltz identity. Okay, and so this wraps up this second section on the optional stopping time and some application to random walks. So in the next section, we'll discuss inequalities and convergence of martingales.